Good evening, and welcome to Cozy Sleep Time. Before we begin tonight's story, take a quiet moment to settle in and get comfortable. Find a position where your body can fully relax, whether you're lying in bed, resting on a couch, or simply unwinding after a long day. Allow your shoulders to soften. Let your breathing slow down just a little. There is nowhere else you need to be, and nothing else you need to do. Here, on Cozy Sleep Time, we explore calm and gentle topics, stories designed to help the mind slow down and drift peacefully toward rest. Each story moves slowly, gently, allowing your thoughts to wander and your body to relax more and more. Our story tonight is about volcanoes, Earth's inner fire. As the story unfolds, you can simply listen, or you can allow your mind to drift. There is no need to stay focused. If your thoughts wander, that is perfectly natural. So take one more slow breath, get comfortable, and let the quiet story begin. How volcanoes form deep beneath our feet, far below the solid ground we walk on, exists a world of intense heat and constant change. Our planet's interior is not the cold, static place we might imagine, but rather a dynamic realm where temperatures climb high enough to melt rock itself. It is in this hidden environment that the story of volcanoes begins. To understand how volcanoes form, we must first understand what lies beneath the Earth's surface. The planet is layered like an onion, with a thin outer crust forming the ground we live on, a thick mantle of hot, solid rock beneath it, and an iron core at the center that blazes at temperatures exceeding those on the surface of the sun. The mantle, though technically solid rock, is so hot that over millions of years it can flow and shift like taffy being stretched. It is from this partially melted mantle that volcanoes draw their material. The key substance we need to understand is called magma. Magma is molten rock, a thick mixture of melted minerals and gases that forms deep within the earth when temperatures and pressures reach certain conditions. Magma is lighter than the solid rock around it, and like a bubble rising through water, it gradually makes its way upward through cracks and weaknesses in the earth's crust. When magma manages to reach the surface, it becomes what we call lava, and the moment it breaks through the surface, a volcano is born. Not everywhere on Earth is equally likely to produce volcanoes. The vast majority of volcanic activity occurs along the boundaries where the Earth's tectonic plates meet. These plates are enormous slabs of rock that fit together like a puzzle covering the Earth's surface, and they are constantly moving, though very slowly, at about the speed at which fingernails grow. Where these plates pull apart, magma rises to fill the gap. Where one plate dives beneath another, the heat and pressure cause changes that generate magma. And in a few special places called hotspots, plumes of unusual heat rise from deep within the mantle, creating volcanoes in the middle of tectonic plates far from any boundary. The most common locations for volcanoes are along the Pacific Ring of Fire, a horseshoe-shaped band that circles the edge of the Pacific Ocean. This region contains more than half of the world's active volcanoes, and it is where the Pacific Plate meets many other plates, creating ideal conditions for volcanic activity. Countries like Japan, Indonesia, the Philippines, and the western coasts of North and South America all experience significant volcanic activity because they sit along this ring of fire. There are three main ways that magma can be generated deep within the Earth, each associated with a different geological setting. The first involves diverging plate boundaries, places where two plates are moving away from each other. When this happens beneath the ocean, the crust thins and magma rises to fill the gap, creating new seafloor in a process called seafloor spreading. Iceland sits atop this type of boundary, which is why it has so many volcanoes and and why new land is still being created there today. The second way involves converging plate boundaries, places where one plate is pushed beneath another in a process called subduction. When an oceanic plate dives beneath a continental plate, the descending rock is subjected to immense heat and pressure. Water trapped in the rock gets released, which lowers the melting point of the surrounding material and generates magma. This is why the Andes Mountains, running along the western edge of South America, are dotted with volcanoes. The magma produced in these settings tends to be thicker and more viscous than that produced at spreading centers. The third way involves hotspot volcanism, which occurs in the middle of tectonic plates, far from any boundary. Hotspots are regions where unusually hot material rises from deep within the mantle, perhaps even from near the core mantle boundary. As the tectonic plate moves slowly across this hotspot, a chain of volcanoes is created. The Hawaiian Islands are the most famous example of this process. The oldest islands are farthest from the hotspot, while the newest and still active volcanoes are closest to it. Once magma forms, it does not immediately rush to the surface. It may take thousands or even hundreds of thousands of years for magma to travel from its birthplace deep in the mantle to the surface. Along the way, it collects in chambers called magma chambers, where it can mix with different types of magma and accumulate gases. The composition of the magma can change during this journey as different minerals crystallize and fall out, or as new material melts into the mixture. The journey to the surface is not always successful. Much of the magma that rises through the earth never reaches the surface at all. Instead, it cools and solidifies underground, forming rock formations called intrusions. Only when the pressure and gas content are sufficient does the magma break through to become lava and create a volcanic eruption. The gases dissolved in magma play a crucial role in determining whether an eruption will be gentle or explosive. When magma rises toward the surface, the pressure decreases, allowing the gases to come out of solution, just like carbon dioxide bubbles form when a soda bottle is opened. If the magma is runny and the gases can escape easily, the eruption tends to be relatively calm, with lava flowing gently down the volcano's sides. If the magma is thick and sticky, the gases become trapped and build up pressure until they explode with tremendous force. The shape and size of a volcano depends on the type of magma that creates it and the style of eruption. Shield volcanoes, like those in Hawaii, form from thin, runny lava that flows easily and builds up broad, gently sloping shapes over many eruptions. Stratovolcanoes, like Mount Fuji in Japan, form from thicker, more viscous magma that piles up material near the vent, creating steep, conical mountains. Cinder cones are the smallest type, built from fragments of lava that are thrown into the air and fall back down around the vent. Understanding how volcanoes form is more than an academic exercise. It helps us appreciate the powerful geological forces that shape our planet and reminds us that the ground beneath our feet is far more dynamic than it appears. The next time you see a mountain or look at a map of volcanic regions, you can imagine the ancient processes of heat and pressure that created those remarkable landforms, all beginning with molten rock making its slow journey from the depths of the earth toward the light of day. Types of volcanoes. Not all volcanoes look alike or behave the same way. Just as mountains can have many different shapes and sizes, volcanoes come in several distinct types, each reflecting the geological conditions under which they formed and the nature of the material that built them. The largest and most massive type of volcano is the shield volcano. These giants get their name from their resemblance to a warrior's shield laid flat on the ground, with broad, gently sloping sides that extend for miles. Shield volcanoes form when lava with low viscosity flows easily across the surface, traveling great distances before cooling and solidifying. Because this type of lava spreads out so thinly, the volcano builds up gradually over many eruptions, creating a massive but low profile. The Hawaiian Islands are the textbook example of shield volcanoes. Mauna Loa on the island of Hawaii is the largest active volcano on Earth. It rises more than 30,000 feet from the ocean floor to its summit, making it taller than Mount Everest if measured from its true base. Yet despite its immense size, the slope from its base to its summit is so gentle that many people do not realize they are climbing a mountain at all. The volcano's breadth is equally impressive, covering an area roughly the size of Connecticut. Mauna Loa's neighbor, Mauna Kea, is even taller and stands more than 33,000 feet above its base on the seafloor. Shield volcanoes are characterized by their non-explosive eruptions. Because the magma that feeds them is thin and runny, gases can escape easily from the lava as it flows. This results in relatively gentle eruptions where lava fountains may play spectacularly, but the molten rock primarily flows downhill in rivers of fire. These eruptions rarely cause the violent explosions associated with other volcano types, though they can still be dangerous simply due to the sheer volume of material they produce. In contrast to the gentle giants, stratovolcanoes, also known as composite volcanoes, are the classic conical mountains that most people picture when they think of a volcano. These include famous peaks like Mount Fuji in Japan, Mount Vesuvius in Italy, and Mount Rainier in the United States. Stratovolcanoes are built from layers of hardened lava, volcanic ash, and fragmented rock that accumulate around the vent over thousands of years. Each eruption adds another layer, gradually building the steep, symmetrical cones that characterize this type. The magma that creates stratovolcanoes is quite different from that in shield volcanoes. It contains more silica, which makes it thicker and more viscous. This sticky magma traps gases until pressure builds to the point where it explodes outward. The result is an eruption style that alternates between explosive bursts and flowing lava, creating the layered structure that gives these volcanoes their name. These explosive eruptions can be enormously destructive, blasting clouds of hot ash and rock high into the atmosphere and sending pyroclastic flows rushing down the mountain's flanks. Stratovolcanoes tend to cluster along subduction zones, where one tectonic plate dives beneath another. The collision creates magma with a different chemical composition, richer in silica and volatiles, that fuels the explosive eruptions. The ring of fire around the Pacific Ocean is dotted with stratovolcanoes for this reason. Cinder cones are the smallest and simplest type of volcano. They form when lava is thrown high into the air from a single vent and falls back down as fragments called cinders. These fragments pile up around the vent in a roughly circular cone shape, rarely more than a few hundred feet tall. Because the material is loose and unconsolidated, cinder cones tend to erode quickly and do not last geologically long. Many cinder cones are one-time events, forming during a single eruption that may last weeks or months. Paracutin in Mexico is a famous example that appeared in a farmer's cornfield in 1943 and grew rapidly over the following years. Calderas represent a different kind of volcanic structure, formed not by material building up, but by material being removed. When a massive eruption empties a magma chamber, the volcano's support is gone, and the peak can collapse inward, creating a vast, crater-like depression. Some calderas are dozens of miles across. Crater Lake in Oregon formed about 7,700 years ago when Mount Mazama collapsed after a massive eruption, leaving a crater that eventually filled with rain and snowmelt to create one of the clearest lakes on Earth. The Yellowstone caldera is even larger, covering an area larger than many states. Lava domes are another type of volcanic formation, created when thick, viscous lava barely moves at all as it squeezes out of a vent. Instead of flowing away, it piles up in a rounded mound directly over the vent. Domes can grow very large, but they are notoriously unstable. Because the lava is so sticky, trapped gases cannot escape easily, and pressure can build until the dome collapses explosively, producing dangerous pyroclastic flows. The eruption of Mount St. Helens in 1980 was triggered by the collapse of a growing lava dome. Each volcano type tells a story about its origins. The shape of a volcano encodes information about the type of magma that built it, the style of eruptions that occurred, and the geological setting in which it formed. By studying these different shapes, geologists can understand the history of volcanic regions and better predict how future eruptions might behave. The diversity of volcano types is a reminder of the complex and varied nature of volcanic activity on Earth. From the massive, gentle slopes of Hawaiian shield volcanoes to the dramatic, ash-covered peaks of stratovolcanoes, each type represents a different response to the fundamental forces of heat and pressure deep within our planet. How volcanoes erupt. The moment a volcano comes alive with an eruption is one of the most dramatic events in nature. After months or years of subtle warnings, the mountain awakens in spectacular fashion, sending molten rock, ash, and gases into the atmosphere in displays of raw planetary power. Understanding why and how eruptions happen reveals much about the behavior of the Earth beneath our feet. Volcanic eruptions begin deep underground, in chambers where magma collects before making its way to the surface. These magma chambers are located anywhere from a few miles to dozens of miles beneath the ground. The magma within them is under tremendous pressure from the overlying rock, which keeps the dissolved gases trapped in solution, much like carbon dioxide is trapped in a sealed soda bottle. When the magma finds a path to the surface, either through existing fractures or by creating new ones, the pressure drops dramatically. This pressure release is the fundamental trigger for an eruption. The behavior of an eruption depends heavily on the properties of the magma involved. Magma is not all the same. Its characteristics are determined by its chemical composition, particularly how much silica it contains. Silica is a compound made of silicon and oxygen that forms the backbone of many minerals, and it has a profound effect on how magma behaves. Low silica basaltic magma is thin and runny, like warm honey. Gases can escape from it easily, so when it erupts, the eruption tends to be relatively peaceful. The gas bubbles form and rise through the magma without causing violent explosions. Instead, the magma flows out of the vent and moves down the mountain's slopes, sometimes traveling miles before cooling. This type of eruption produces the gentle, flowing lava rivers characteristic of Hawaiian volcanoes. At the other extreme is high silica rhyolitic magma, which is thick and sticky, like cold caramel. This magma flows very slowly, and the gases trapped within it cannot escape easily. As the magma rises and pressure decreases, the gases come out of solution but become trapped by the viscous material. Pressure builds and builds until suddenly the magma cannot contain it anymore, and the result is a violent explosion. These eruptions can blast millions of tons of material into the sky in a matter of hours. Between these extremes lies andesitic magma, typical of stratovolcanoes, which has intermediate properties. It can produce both flowing lava and explosive eruptions, sometimes within the same eruptive cycle. Volcanologists have developed a classification system for different eruption types, with each type named after a volcano where that behavior was first studied or is most characteristic. Understanding these types helps scientists predict what a particular volcano might do. Hawaiian eruptions are the gentlest type, named for the Hawaiian volcanoes where they are common. These eruptions feature fluid lava that flows easily, sometimes forming rivers of molten rock that travel great distances. Spectacular lava fountains may shoot hundreds of feet into the air, but the overall effect is more like a fountain than an explosion. When the lava flows over already cooled rock, it can create unusual textured surfaces like paho, which looks like draped cloth, or which is rough and jagged. Strombolian eruptions, named after the Italian island of Stromboli, are characterized by regular bursts of activity. These eruptions involve moderate explosions that throw clots of incandescent lava into the air. The explosions occur at regular intervals, ranging from seconds to minutes apart, creating a pattern of activity that can continue for hours or even days. The material thrown out typically falls back down onto the volcano's flanks, building up the slopes over time. Volcanian eruptions are more violent than Strombolian, named after the Italian island of Volcano. These eruptions involve thick magma that cannot flow easily. When pressure builds sufficiently, the volcano blasts out dense clouds of ash and volcanic rock with tremendous force. Between eruptions, the volcano may be quiet, building up pressure for the next outburst. Mount Pelée in the Caribbean and Mount St. Helens in the United States have produced Vulcanian-style eruptions. Plinian eruptions are the most violent type, named after Pliny the Younger, who described the famous eruption of Mount Vesuvius in 79 AD. These eruptions are characterized by enormous columns of ash and gas that extend high into the atmosphere, sometimes reaching heights of more than 25 miles. The eruption of Mount St. Helens in 1980 was a Plinian event, sending a column of ash across much of the United States. The 1991 eruption of Mount Pinatubo in the Philippines injected so much material into the atmosphere that global temperatures temporarily dropped slightly. The explosivity of an eruption is measured on the Volcanic Explosivity Index, or VEI, a scale from 0 to 8 that roughly corresponds to the volume of material ejected. Each increase in the scale represents a 10-fold increase in the volume of ejecta. Most eruptions are VEI 0 or 1, while truly catastrophic events like the eruption that formed Crater Lake in Oregon or the Krakatoa eruption of 1883 are rated VEI 6 or 7. What determines whether an eruption will be gentle or explosive? Scientists have identified 4 main factors. First is the amount of gas dissolved in the magma. More gas means more potential for explosive behavior. Second is the viscosity of the magma. Thicker magma traps gas more effectively, building pressure. Third is the rate at which pressure is released. If magma rises quickly, gases may not have time to escape peacefully. Fourth is the number of places where gas bubbles can form. More nucleation sites means more bubbles, which can lead to more energetic behavior. The same volcano can produce different types of eruptions at different times in its history. As magma composition changes, or as the plumbing system of the volcano evolves, the style of activity can shift dramatically. This is one of the reasons volcanoes are so challenging to study and predict. Eruptions can also have significant impacts on the surrounding environment and even the global climate. Large eruptions inject sulfur dioxide into the atmosphere, where it reacts with water vapor to form tiny droplets that reflect sunlight. Major eruptions can cause measurable cooling of global temperatures for a year or more. They also produce ash that can bury crops, damage infrastructure, and pose health hazards to humans and animals. Despite their destructive potential, eruptions are also beneficial over geological time. Volcanic ash weathers into rich soil that supports agriculture. Volcanic processes create new landmass, building islands like Hawaii literally from the ocean. And the gases released during eruptions, particularly water vapor and carbon dioxide, have helped shape Earth's atmosphere over billions of years. Understanding how and why volcanoes erupt is a window into the powerful forces that continue to shape our dynamic planet: magma and lava. At the heart of every volcanic eruption lies a substance of extraordinary complexity. Magma and its surface counterpart, lava, are the materials that build volcanoes and shape the landscapes around them. Understanding these molten rocks reveals much about the dynamic processes occurring deep within our planet. Magma is not simply melted rock. It is a complex mixture of molten minerals, dissolved gases, and crystalline solids, all existing together at temperatures that would destroy ordinary materials. The temperature of magma varies depending on its composition, but it generally ranges from about 1,300 to 2,400 degrees Fahrenheit. To put this in perspective, the hottest temperature most humans ever experience is the flame of a propane torch, which reaches only about 3,100 degrees. Magma is hot enough to melt most metals and would destroy any living thing that touched it. The key to understanding magma lies in its chemical composition. Magma is primarily composed of oxygen and silicon, which combine to form silica tetrahedra, the building blocks of many common minerals. The amount of silica in magma determines most of its important properties, including its melting temperature, its viscosity, and how it behaves during an eruption. Basaltic magma, with relatively low silica content, melts at higher temperatures but flows easily. It is the most common type of magma on Earth, originating from the partial melting of the mantle. Basaltic magma typically contains less than about 52% silica, making it relatively fluid. When it erupts, it can travel long distances, flowing like thick syrup down the slopes of a volcano and sometimes covering many miles of terrain. Andesitic magma, found typically at subduction zone volcanoes, contains about 52% to 63% silica. This intermediate composition makes it more viscous than basaltic magma, and it tends to produce more explosive eruptions. The higher silica content means the magma holds more water and other gases, which become explosive when pressure is released. Rhyolitic magma, with more than 63% silica, is the most viscous type. It flows very slowly, almost like paste, and can trap gases effectively until pressure builds to explosive levels. Rhyolitic eruptions are among the most violent natural disasters on Earth, capable of destroying entire mountain ranges and altering global climate. Beyond silica, the other crucial component of magma is gas. Magma contains dissolved gases, primarily water vapor, carbon dioxide, and sulfur dioxide. These gases are dissolved in the magma under high pressure, but come out of solution as the magma rises toward the surface, just like carbon dioxide bubbles form when opening a soda can. The type and amount of gas greatly influences how an eruption will behave. Water vapor is the most common gas in magma, sometimes making up more than 3% of the total weight. When released, it can create powerful steam explosions, especially if the magma comes into contact with groundwater or surface water. Carbon dioxide is also abundant and can be released peacefully or explosively depending on conditions. Sulfur dioxide is particularly important because it reacts with the atmosphere to create aerosols that can reflect sunlight and affect climate. The transition from magma to lava occurs the moment molten rock reaches the surface. Though the temperature remains essentially the same, the change in environment causes significant changes in behavior. On the surface, lava loses heat to the air and ground, forming a crust that eventually solidifies. Unlike magma, which is contained under pressure, lava is exposed to the atmosphere and its behavior changes accordingly. Lava comes in two main types with very different textures. Pahiho is a Hawaiian term for smooth, ropey lava that forms when a relatively fluid flow moves across the surface. The outer skin remains flexible as the molten interior continues to flow beneath, creating beautiful twisted patterns. Is a term for rough, jagged, clinkery lava that forms when more viscous lava flows break apart into sharp fragments. Walking on is extremely painful, as the fragments are very sharp. The temperature of flowing lava varies considerably. Basaltic lava typically emerges at temperatures between 2,000 and 2,200 degrees Fahrenheit. As it flows and cools, it becomes more viscous, eventually stopping completely at temperatures around 1,800 to 2,000 degrees. Lava can remain molten for remarkable distances, however, continuing to flow for days or even weeks in some cases. When lava cools and solidifies, it forms various types of volcanic rock. Basalt is the most common, forming from rapid cooling of lava at the surface. Obsidian forms from lava that cools so quickly that no crystals can form, creating the glass-like volcanic rock prized by collectors. Pumice forms from frothy lava full of gas bubbles, lightweight enough to float on water. The study of magma and lava helps scientists understand not only volcanic eruptions, but also the fundamental processes occurring deep within the Earth. By analyzing the chemical composition of lava samples, geologists can determine the conditions deep underground where the magma originated and the journey it took to reach the surface. This information helps predict future volcanic activity and understand the Earth's internal dynamics. The physical properties of magma and lava also influence what happens after an eruption. The composition affects not just the immediate eruption style, but also the long-term effects on the landscape. Basaltic flows create fertile soils over time, while rhyolitic eruptions can devastate huge areas with ash and pyroclastic flows. Understanding magma and lava is essential for anyone seeking to comprehend the powerful geological forces that continue to shape our dynamic planet. Famous volcanic eruptions. Throughout human history, volcanic eruptions have shaped civilizations, altered ecosystems, and left indelible marks on the landscape. Some eruptions have been so powerful they affected the entire globe, while others were more localized but still devastating. Examining famous eruptions helps us understand the power these events unleash and the lasting impacts they leave behind. The eruption of Mount Vesuvius in 79 AD stands as one of the most famous volcanic events in history. Located near the Bay of Naples in Italy, Vesuvius had been considered extinct by the Romans, its slopes covered with vineyards and towns. When it erupted in late summer, the people of Pompeii and Herculaneum had no warning of the catastrophe about to unfold. The eruption sent a massive column of pumice and ash skyward, which then collapsed in pyroclastic surges that swept down the mountain slopes at speeds exceeding 100 miles per hour. In less than 24 hours, both cities were buried under volcanic material. Thousands of people died, their bodies preserved in the ash until discovered nearly 2,000 years later by archaeologists. The eruption was so powerful that it created the caldera that exists today and darkened the sky across the Roman Empire. In 1883, the volcanic island of Krakatoa in Indonesia erupted in one of the most violent explosions in recorded history. The initial eruption was heard thousands of miles away and triggered massive tsunamis that crashed into nearby islands, killing more than 36,000 people. The eruption column reached into the stratosphere, injecting enormous amounts of sulfur dioxide into the atmosphere. Global temperatures dropped, and spectacular sunsets appeared around the world for years afterward. The island itself was largely destroyed, collapsing into an underwater caldera. What makes this eruption particularly well studied is the extensive documentation from the era, including telegraphic reports from colonial outposts around the world. The 1980 eruption of Mount St. Helens in Washington state brought volcanic danger home to the American consciousness. For weeks before the main eruption, the mountain had been convulsed with earthquakes and bulging visibly as magma pushed against its side. When the eruption finally came on May 18th, it was triggered not by an explosion from the top, but by a landslide that released the pressure holding back the magma. The resulting lateral blast devastated an area of more than 230 square miles, flattening millions of trees. The vertical eruption column reached 80,000 feet into the air, spreading ash across 11 states. The eruption killed 57 people and caused billions of dollars in damage, becoming the most economically destructive volcanic eruption in American history. Mount Pinatubo in the Philippines erupted in 1991 after lying dormant for nearly 500 years. The eruption was one of the largest of the 20th century, producing a column of ash that rose more than 22 miles into the atmosphere. More than 300 people died, but accurate forecasts and evacuations saved tens of thousands of lives. The sulfur dioxide injected into the atmosphere circled the globe, causing global temperatures to drop by about 0.9 degrees Fahrenheit over the following 15 months. The eruption also created a massive lahar, a volcanic mudflow that buried entire communities and continued to pose dangers for years afterward. The eruption of Tambora in 1815 holds the record for the most powerful volcanic eruption in recorded history. Occurring on the island of Sumbawa in Indonesia, the eruption produced a column more than 30 miles high and a pyroclastic flow that devastated the surrounding area. Approximately 71,000 people died directly from the eruption, while tens of thousands more died in the aftermath from starvation and disease. The volcanic dust injected into the atmosphere created spectacular sunsets worldwide and caused 1816 to become known as the year without a summer, with snow falling in June in New England and widespread crop failures across Europe. Perhaps the most catastrophic eruption in human prehistory occurred at Toba in Sumatra about 74,000 years ago. The eruption was so powerful, it may have reduced the human population to just a few thousand individuals, leaving a genetic bottleneck that some scientists believe is still visible in human DNA today. The Toba eruption produced a volcanic winter that lasted for years, dramatically cooling the planet and potentially triggering an ice age. These eruptions, while devastating, are just moments in the much longer history of volcanic activity on Earth. The geological record shows eruptions far larger than any human has witnessed, events that shape the continents and the atmosphere. Studying these historical eruptions helps scientists understand what might happen in the future and prepares us for the inevitable volcanic activity yet to come. Volcanic hazards. Volcanoes are not just spectacular natural displays. They represent genuine dangers to human populations and infrastructure. Understanding the various hazards associated with volcanic activity helps communities prepare and respond appropriately when volcanoes come alive. Lava flows are perhaps the most recognizable volcanic hazard, though they are also among the least deadly. Lava moves slowly enough that people can usually escape, but it destroys everything in its path. The extreme heat and physical force of flowing lava incinerates buildings, sears vegetation, and melts vehicles. Lava flows cover land permanently, replacing existing ecosystems with new volcanic rock. The 2018 eruption in Hawaii produced lava flows that destroyed hundreds of homes and reshaped the coastline, adding new land to the island while taking existing property. Volcanic ash poses different challenges. Ash consists of tiny fragments of rock and glass, produced when magma is blasted apart during explosive eruptions. Unlike wood ash from a fireplace, volcanic ash is extremely hard and abrasive, capable of scratching glass and damaging machinery. Ash can collapse buildings when accumulated in sufficient quantities, contaminate water supplies, and pose serious health risks when inhaled. The 2010 eruption of Eyjafjallajökull in Iceland produced ash that disrupted airline flights across Europe for weeks, stranding millions of passengers and causing billions of dollars in economic damage. Pyroclastic flows represent one of the most dangerous volcanic phenomena. These superheated clouds of gas, ash, and rock fragments sweep down volcanic slopes at speeds exceeding 100 miles per hour, with temperatures hot enough to cause severe burns through clothing. There is no escape from a pyroclastic flow. Anything in its path is destroyed. The 1902 eruption of Mount Pelée in Martinique sent a pyroclastic flow into the city of Saint-Pierre, killing approximately 30,000 people in just minutes. Entire cities and their populations have been erased in moments by these devastating flows. Lahars, also known as volcanic mud flows, are mixtures of water, ash, and debris that behave like liquid concrete. They can be triggered by rapid melting of snow and ice during an eruption, by heavy rainfall, or by the collapse of volcanic crater lakes. Lahars flow through river valleys with tremendous force, destroying bridges, buildings, and anything else in their path. The 1985 eruption of Nevado del Ruiz in Colombia triggered a lahar that buried the city of Armero, killing approximately 23,000 people. Many victims had been warned but did not evacuate, highlighting the importance of emergency preparedness. Volcanic gases, though invisible, can be deadly. Carbon dioxide and hydrogen sulfide are particularly dangerous because they can accumulate in low-lying areas, displacing oxygen and causing suffocation. The Lake Nyos disaster in Cameroon in 1986 was caused not by an eruption but by a limnic eruption, when carbon dioxide dissolved in a crater lake suddenly erupted, creating a cloud that rolled down surrounding valleys, killing nearly 1,700 people. Even relatively minor gas emissions can cause respiratory problems for local populations and contribute to acid rain. Volcanic tsunamis are generated when eruptions cause landslides into the ocean or when pyroclastic flows enter the water. The 1883 eruption of Krakatoa produced tsunamis more than 100 feet high that crashed onto nearby islands, causing most of the deaths from that catastrophic event. Coastal communities near volcanic islands face this additional hazard that combines volcanic and oceanic forces. Beyond immediate dangers, volcanoes can cause longer-term impacts on climate and agriculture. Large eruptions inject sulfur dioxide into the stratosphere, where it forms aerosols that reflect sunlight and cause cooling. The 1991 eruption of Mount Pinatubo temporarily global temperatures to drop by nearly a degree Fahrenheit. Volcanic ash and sulfur dioxide can also damage crops, contaminate water supplies, and cause respiratory illness that persists long after the eruption ends. Scientists work constantly to improve warning systems for volcanic hazards. Modern monitoring uses seismometers to detect earthquakes caused by magma movement, gas monitors to track emissions, GPS receivers to measure ground deformation, and satellite imagery to track thermal anomalies and ash clouds. These tools have greatly improved our ability to evacuate communities before eruptions, saving countless lives. Understanding volcanic hazards is essential for the millions of people who live in volcanic regions. With proper preparation and respect for these powerful natural forces, communities can reduce risk while still benefiting from the rich volcanic soils and other resources that volcanic regions provide. Monitoring volcanoes. Beneath the surface of every active volcano lies a complex system of moving magma, accumulating pressure and building tension. Volcanologists have developed increasingly sophisticated methods to detect the subtle signs that precede an eruption, allowing communities time to prepare and evacuate when necessary. The primary tool for volcano monitoring is seismology, the study of earthquakes. As magma forces its way through rock underground, it creates distinctive vibrations that differ from typical tectonic earthquakes. These volcanic earthquakes often occur in swarms, with many small quakes happening over a short period, rather than the main shock followed by aftershocks seen in regular earthquakes. Before an eruption, the frequency and intensity of these earthquakes typically increases dramatically as magma fractures its way toward the surface. The Global Positioning System, GPS, has revolutionized volcano monitoring by allowing scientists to measure precisely how the ground deforms as magma accumulates underground. When magma enters a chamber, it pushes the surrounding rock outward, causing the surface to bulge and shift. By placing GPS receivers around a volcano and measuring their positions repeatedly, scientists can create detailed maps of deformation that reveal where magma is accumulating and how much pressure is building. Satellite radar provides another way to track ground deformation, with the advantage of being able to monitor remote volcanoes without installing equipment on site. By comparing radar images taken at different times, scientists can detect changes in the surface elevation of a volcano, sometimes measuring deformation as small as a few millimeters. Gas monitoring offers direct insight into the chemistry of what is happening underground. Magma contains dissolved gases that escape when pressure decreases, and the type and amount of gas emitted can indicate what is happening deep within the volcano. Sulfur dioxide, carbon dioxide, and hydrogen sulfide are all measured, with changes in their ratios or amounts potentially signaling that new magma is rising toward the surface. Thermal monitoring detects the heat associated with magma close to the surface. Infrared satellite imagery can reveal hot spots on a volcano's flanks or summit that indicate areas where magma or hot rocks are near the surface. Temperature increases can sometimes be detected before other signs appear. The key to effective volcano monitoring is combining multiple types of data to build a complete picture of what is happening. A volcano might show seismic activity, but no gas emissions or deformation without earthquakes. By tracking all these signals together, scientists can better understand what is happening and make more accurate predictions. Volcano observatories around the world maintain constant watch over active volcanic regions. The United States Geological Survey operates observatories for the Cascade volcanoes in the Pacific Northwest, the Hawaiian volcanoes, and the Alaska volcanic arc. Similar organizations exist in Japan, Italy, Indonesia, and many other volcanically active nations. One of the most successful examples of volcano monitoring saved thousands of lives in Colombia in 1985. Before the eruption of Nevado del Ruiz, scientists had been tracking increasing seismic activity and deformation for months. When the eruption finally occurred, warnings were issued, but they did not reach the town of Armero in time, and nearly 23,000 people died in the resulting lahar. In the years since, improved communication and monitoring have allowed successful evacuations at many volcanoes around the world. Modern technology continues to improve volcano monitoring capabilities. Drone-mounted instruments can sample gases directly above vents without putting people at risk. Machine learning algorithms help sift through vast amounts of monitoring data to detect patterns that might indicate impending eruptions. Networked sensors can provide real-time data from even the most remote volcanoes. Despite these advances, predicting exactly when a volcano will erupt remains challenging. Scientists can often identify when a volcano is building toward an eruption, but the exact timing can be difficult to determine. Some volcanoes give weeks or months of warning, while others show only hours. The goal of monitoring is not perfect prediction, but rather enough information to allow evacuation of at-risk areas before it is too late. The investment in volcano monitoring has saved countless lives and continues to improve as technology advances. For the millions of people living in the shadow of active volcanoes, these silent watchers provide an essential safety net. Volcanoes and life on Earth. Volcanoes are often thought of as forces of destruction, and indeed they can be devastating in the short term. But over the long sweep of geological time, volcanoes have been essential for life on Earth, playing crucial roles in creating the atmosphere we breathe, the oceans we inhabit, and the fertile soils that sustain our food. The Earth itself was born from volcanic activity. In the earliest days of the planet, about 4.5 billion years ago, the surface was molten, constantly bombarded by debris from space, and continuously reshaped by eruptions. As the planet slowly cooled, volcanoes remained the dominant geological force, releasing gases from the interior that formed the early atmosphere. Without these volcanic emissions, Earth might have remained a lifeless rock like Mars or Venus. The atmosphere we breathe today is largely a product of volcanic activity. When Earth first formed, it had little or no atmosphere. Over billions of years, volcanoes released enormous amounts of carbon dioxide, water vapor, nitrogen, and other gases. The water vapor eventually condensed to form the oceans, while carbon dioxide was eventually incorporated into limestone rocks and removed from the atmosphere. The relatively small amount of carbon dioxide remaining, along with nitrogen and trace gases, creates the atmosphere that supports life as we know it. Volcanic islands like Hawaii demonstrate how new ecosystems arise on barren rock. When lava cools and solidifies into new rock, it initially supports no life at all. Over time, lichens and mosses colonize the surface, breaking down the rock and creating the first thin layer of soil. These pioneer species die and decompose, adding organic matter. Eventually, seeds arrive, carried by birds or wind, and the first plants take root. Each generation adds more organic matter to the soil, and after thousands of years, lush ecosystems cover what was once bare rock. The richness of volcanic soil is legendary. The slopes of volcanoes around the world support productive agriculture precisely because volcanic ash and lava weather into soils packed with nutrients. Indonesia, Japan, Italy, and many other volcanic regions support dense populations because the soil is so fertile. The ancient Roman civilization grew wealthy on the rich soils surrounding Vesuvius, and farmers continue to work those same fields today, despite the obvious danger. Volcanoes also influence the ocean ecosystems that produce half the oxygen we breathe. Volcanic activity on the ocean floor creates hydrothermal vents that support unique communities of organisms never dependent on sunlight. These deep-sea ecosystems are based on chemosynthesis, where bacteria use the chemical energy from volcanic minerals to produce organic matter, supporting tube worms, clams, and other creatures. These vents may represent how life first began on Earth, and similar processes may be occurring on other worlds in our solar system. The sulfur and other elements released by volcanoes also fertilize the oceans. Dust from volcanic eruptions that settles on the ocean surface provides essential nutrients for phytoplankton, the microscopic plants that form the base of marine food webs. Some researchers have suggested that deliberately adding volcanic dust to ocean regions could help combat climate change by stimulating phytoplankton growth that absorbs carbon dioxide from the atmosphere. Volcanic activity has also shaped the course of evolution. Major eruptions that released enormous amounts of material into the atmosphere have caused mass extinctions, clearing the way for new species to arise. The dinosaur-killing asteroid impact that occurred 66 million years ago triggered massive volcanic activity that may have contributed to the extinction. Yet volcanic activity also creates new habitats and drives species to adapt, leading to increased biodiversity over geological time. Perhaps most remarkably, volcanic environments may harbor life on other worlds. Jupiter's moon Europa appears to have a liquid ocean beneath its icy crust, kept warm by tidal forces that generate volcanic activity on the ocean floor. Saturn's moon Enceladus has similar features. If life exists in those subsurface oceans, it would be microbial life that exists in conditions similar to Earth's hydrothermal vent communities, organisms that thrive in the absence of sunlight in temperatures that would seem hellish to us. Volcanoes remind us that our planet is alive in profound ways. The same forces that destroy can also create, and the long-term relationship between volcanoes and life is one of coevolution and mutual influence. Far from being merely agents of catastrophe, volcanoes are essential to the ongoing processes that make Earth habitable. Volcanic rocks and minerals. When lava cools and solidifies, it creates some of the most common and geologically important rocks on Earth. Volcanic rocks and the minerals they contain tell stories of the Earth's interior, preserve records of past eruptions, and provide valuable resources that societies have used for thousands of years. Basalt is the most abundant volcanic rock on Earth, covering vast areas of the ocean floor and forming many volcanic islands. It forms from lava that cools relatively quickly at the surface, allowing only tiny crystals to form. The result is a fine-grained, dark rock that appears black or dark gray in most cases. Basalt makes up the entire ocean floor, created at mid-ocean ridges where tectonic plates spread apart and magma rises to fill the gap. Andesite is another common volcanic rock, named for the Andes Mountains where it is frequently found. It forms from magma of intermediate composition, typically at subduction zone volcanoes. Andesite has more silica than basalt, making it darker in color with visible crystals of minerals like feldspar and amphibole. The presence of andesite often indicates that a volcano is located near a subduction zone. Rhyolite represents the most silica-rich volcanic rocks, forming from viscous magma that cools quickly. It is often light-colored, ranging from pink to gray to white, and typically contains visible quartz and feldspar crystals. Rhyolite eruptions are often explosive because of the high gas content of the magma. Despite being common on continents, rhyolite is much less abundant than basalt. Obsidian forms when lava cools so quickly that no crystals can form at all, creating natural volcanic glass. The rapid cooling prevents atoms from organizing into the orderly patterns that define minerals, leaving a glassy material instead. Obsidian is always black or very dark, though it can appear translucent at thin edges. Its conchoidal fracture, curved and smooth like broken glass, made it valuable for tools and weapons throughout human prehistory. Pumice is another volcanic glass, but one full of holes. It forms when lava containing dissolved gas cools so quickly that the gas comes out of solution as bubbles but cannot escape. The result is a lightweight rock full of cavities, so buoyant it can float on water. Pumice is widely used as an abrasive in soaps, cleaning products, and personal care items. Scoria is similar to pumice but darker and heavier. It forms when gas-rich basaltic magma erupts, creating a rock full of holes, but with a coarser texture than pumice. Scoria is often used as decorative rock in landscaping and as aggregate in concrete. Tuff forms from volcanic ash that has been compacted and cemented together over time. It is a sedimentary rock of volcanic origin, deposited by ash falls from eruption columns or by pyroclastic flows. Tuff is common near major volcanic centers and has been used as a building stone in many regions. Volcanic rocks contain many different minerals, each forming under specific conditions. Feldspar minerals, including orthoclase, plagioclase, and others, are among the most common. They are typically light-colored and form the framework of many volcanic rocks. Pyroxene and amphibole minerals, dark green to black, are common in basalt and andesite. Olivine, bright green, is characteristic of basaltic rocks. Quartz, one of the most familiar minerals, appears in rhyolite as well-formed crystals. The minerals in volcanic rocks provide clues about their origins. The presence of certain minerals tells geologists about the temperature and pressure at which the magma formed, how long it traveled through the earth, and how quickly it cooled. By studying these minerals, scientists can reconstruct the history of volcanic events and better understand the Earth's interior. Beyond their scientific importance, volcanic rocks and minerals have practical applications. Basalt is crushed for use as aggregate in roads and concrete. Pumice is used in industry and personal care. Obsidian has been used for jewelry and decoration for thousands of years. Tuff has been used as building stone, including in ancient Rome, where it was a primary construction material. The study of volcanic rocks and minerals connects the deep earth to the surface, linking the processes happening far below our feet to the landscapes we see around us. Every piece of volcanic rock is a sample of the Earth's interior, preserved for scientific study. Supervolcanoes and massive eruptions. While most volcanic eruptions are relatively small events, a few extraordinary eruptions in Earth's history have been cataclysmic beyond human experience. These rare events, called supereruptions, are among the most powerful phenomena on our planet and have shaped the course of life on Earth. A supervolcano is not a single mountain, but a large volcanic system capable of producing supereruptions, events that eject more than 1,000 cubic kilometers of material. To put this in perspective, the 1980 eruption of Mount St. Helens ejected about 1 cubic kilometer of material. A supereruption is 1,000 times larger. Such eruptions are rare, occurring roughly every 100,000 years or so, but when they happen, they dramatically reshape the landscape and can affect global climate. Yellowstone is perhaps the most famous supervolcano, with a caldera spanning a vast area of Wyoming, Montana, and Idaho. The Yellowstone system has produced 3 supereruptions in the past 2.1 million years, each one releasing enormous amounts of material and collapsing to form the caldera seen today. The most recent supereruption, about 640,000 years ago, released roughly 1,000 cubic kilometers of material and created the current Yellowstone caldera. The Toba eruption, occurring about 74,000 years ago in Sumatra, is the largest volcanic eruption in the past 2 million years. It released approximately 2,800 cubic kilometers of material, more than double what Yellowstone produced in its most recent supereruption. The Toba eruption created a volcanic winter that lasted for years, with global temperatures dropping dramatically. Some scientists believe the eruption caused a genetic bottleneck in the human population, reducing our ancestors to just a few thousand individuals. The Long Valley caldera in California represents another supervolcano system, having produced a massive eruption about 760,000 years ago that released roughly 600 cubic kilometers of material. The area remains seismically active today, with magma still present beneath the surface. Scientists monitor the region constantly, watching for signs of future activity. What makes these eruptions so powerful? Unlike typical volcanoes that build up over many smaller eruptions, supervolcano systems involve massive magma chambers that can extend for miles underground. When the pressure in these chambers finally releases, the eruption is cataclysmic, producing pyroclastic flows that cover thousands of square miles and ash that falls across the continent. The eruption column from a supereruption would extend into the stratosphere, injecting enormous amounts of sulfur dioxide and dust into the atmosphere. The effects of a supereruption would be global. Within hundreds of miles of the eruption, everything would be buried under thick ash. Hundreds of miles farther, pyroclastic flows would destroy everything in their path. The ash would collapse roofs, clog roads, contaminate water supplies, and damage machinery. Air travel would be disrupted for months or years as ash circles the globe. Global climate effects would be severe. The sulfur dioxide injected into the atmosphere would form aerosols that reflect sunlight, causing temperatures to drop dramatically. The effect could last for years, potentially triggering crop failures and food shortages worldwide. The 1991 eruption of Pinatubo, a much smaller event, caused global temperatures to drop by nearly a degree Fahrenheit. A supereruption could cause cooling of 10 degrees or more, creating conditions similar to a minor ice age. Despite their destructive potential, supereruptions are extremely rare. The odds of one occurring in any given year are very low, and scientists monitor known supervolcano systems closely for any signs of unusual activity. While Yellowstone shows some signs of unrest, including earthquakes and ground deformation, these are normal for an active geological system and do not indicate an imminent eruption. If a supereruption were to occur today, evacuation zones would need to extend hundreds of miles from the volcano. Global coordination would be essential for managing the ash fallout and climate effects. Scientists are working to better understand these systems and improve prediction capabilities. The study of supervolcanoes reminds us of the true scale of geological forces. While individual volcanoes are impressive, the largest volcanic events are almost beyond comprehension, capable of altering the course of evolution and reshaping the planet itself. Volcanoes beyond Earth. Volcanoes are not unique to Earth. Our solar system contains numerous worlds with volcanic activity, some of which are far more volcanically active than our planet. Exploring these alien volcanoes helps scientists understand volcanic processes across the universe and raises intriguing questions about the potential for life elsewhere. Mars hosts the largest volcano in the solar system, Olympus Mons, standing nearly 22 miles high and covering an area roughly the size of France. This massive shield volcano was built by countless eruptions of fluid lava over billions of years. Mars also contains many other volcanic features, including extensive lava plains and smaller volcanoes scattered across the planet. The key difference is that Mars has no plate tectonics, so volcanic activity remained concentrated in a few locations, allowing the volcanoes to grow far larger than any on Earth. Venus is arguably the most volcanically active world in the solar system, with thousands of volcanic features scattered across its surface. The planet has numerous shield volcanoes, vast lava plains, and strange dome-like features called coronae that may form from upwelling mantle plumes. Radar observations from orbiting spacecraft have revealed evidence of recent lava flows, and the planet's thick atmosphere contains elevated sulfur levels suggesting active volcanic outgassing. Io, one of Jupiter's moons, is the most volcanically active body in the solar system. Its surface is constantly reshaped by eruptions, with hundreds of active volcanoes producing spectacular plumes of sulfur and sulfur dioxide that rise hundreds of miles into space. Io's volcanic activity is driven by tidal heating, as the moon's interior is squeezed and stretched by Jupiter's powerful gravity and the gravitational pull of Jupiter's other moons. The heat generated by this constant kneading melts rock deep within Io, fueling eruptions that are far more frequent than anything seen on Earth. Enceladus, a small moon of Saturn, displays cryovolcanic activity, a different kind of volcanism that involves water and other volatile compounds rather than molten rock. Geysers at its south pole spray water vapor, ice particles, and organic molecules into space from a subsurface liquid water ocean. This makes Enceladus one of the most promising places in the solar system for potential life, as the ingredients for biology appear to be present in its hidden ocean. Europa, another Jupiter moon, likely has similar cryovolcanic activity beneath its icy surface. The moon is squeezed by tidal forces, generating heat that may keep a subsurface ocean liquid and could drive volcanic activity on the ocean floor. If life exists in Europa's ocean, it would be in conditions similar to Earth's deep-sea hydrothermal vent communities. The process of studying extraterrestrial volcanoes has taught scientists much about volcanic processes in general. Observations of Io have revealed that volcanoes can exist in configurations not seen on Earth, with lava lakes and powerful plumes being common. The study of Martian volcanoes helps scientists understand how volcanic activity works in the absence of plate tectonics. Understanding volcanoes on other worlds also informs the search for life beyond Earth. Volcanic activity provides energy and nutrients that could support biological processes. The presence of active volcanism increases the likelihood that a world is geologically alive and potentially habitable. Future exploration of these volcanic worlds promises to reveal even more. Proposed missions to Io and Europa would provide closer views of their volcanic activity and perhaps sample the materials being ejected into space. The James Webb Space Telescope has already observed Io's volcanic activity from orbit around Earth, demonstrating how observations can be made from great distances. Volcanoes, it turns out, may be among the most common geological processes in the universe. Wherever there is sufficient internal heat and suitable materials, volcanic activity is likely to occur. This makes the study of Earth's volcanoes not just a matter of understanding our own planet, but a window into the geological processes that may be occurring across the cosmos. Volcanic islands and seafloor spreading. The ocean floor is not the static landscape we might imagine, but a dynamic region where new crust is constantly being created and destroyed. Much of this volcanic activity occurs far from human observation, hidden beneath miles of water. Yet its effects shape our planet profoundly, creating new land masses and cycling material from the Earth's interior back to the surface. Mid-ocean ridges represent the most extensive volcanic system on Earth, circling the globe like seams on a baseball. These underwater mountain ranges extend for more than 40,000 miles, marking the boundaries where tectonic plates pull apart and new ocean crust is born. Along these ridges, Magma rises from the mantle below, erupting onto the seafloor, where it cools and solidifies to form new basaltic crust. This process, called seafloor spreading, has been operating for billions of years and continues today. Iceland stands as the only place on Earth where a mid-ocean ridge rises above sea level, making it a unique natural laboratory for studying seafloor spreading processes. The island sits directly on the mid-Atlantic ridge, and as the North American and Eurasian plates pull apart, new volcanic material fills the gap. The result is an island that is literally growing, with new land being created through volcanic activity, even as existing rock is torn apart by earthquakes. The volcanic activity on Iceland is continuous and dramatic. The island experiences frequent eruptions, with lava flows sometimes covering roads and threatening communities. The 2010 eruption of Eyjafjallajökull gained worldwide attention when its ash cloud disrupted air travel across Europe for days. Yet the volcanic activity also creates benefits, including abundant geothermal energy that powers much of the island and hot springs that attract visitors from around the world. Volcanic islands form in various ways. Hotspot volcanoes create chains like the Hawaiian Islands, where a stationary plume of hot material beneath the tectonic plate creates volcanoes that eventually drift away from their heat source. As the plate moves, the hotspot creates a chain of islands, with the oldest farthest from the hotspot and the youngest directly above it. The Hawaiian chain extends far beyond the visible islands, with underwater seamounts and islands continuing the pattern northwestward. Other volcanic islands form at subduction zones, where one tectonic plate dives beneath another. The Japanese archipelago, the Philippines, and the Indonesian archipelago all sit along subduction zones, with volcanic activity driven by the interaction of the plates. These island chains often feature some of the most dangerous volcanoes on Earth, including Mount Fuji and the many volcanoes that dot the Indonesian archipelago. The creation of new volcanic islands is a dramatic process that humans have witnessed in recent history. In 1963, an undersea eruption near Iceland built a new island called Surtsey, which rose from the ocean in spectacular fashion. Scientists have studied Surtsey continuously since its formation, watching as pioneer species colonized the barren rock and simple ecosystems developed from scratch. The island is now a UNESCO World Heritage Site, preserved as a natural laboratory for ecological succession. Similarly, the island of Hunga Tonga Hunga Ha'apai appeared in the Pacific Ocean in 2014 from an undersea volcanic eruption. It grew to about 400 acres before partially collapsing in a subsequent eruption in 2022. These newly formed islands demonstrate the dynamic nature of Earth's surface and the ongoing geological processes that continue to reshape our planet. The deep-sea volcanic environments known as hydrothermal vents represent another form of volcanic activity occurring far beneath the ocean's surface. Where magma heats seawater that has seeped into the seafloor, superheated water rich in minerals erupts back into the cold ocean, creating chimneys of precipitate minerals. These vents support unique ecosystems that depend not on sunlight, but on chemical energy from the Earth, hosting bacteria, tube worms, clams, and other organisms that exist nowhere else. The study of seafloor volcanic processes has revealed much about how Earth's crust is created and recycled. The pattern of magnetic stripes on the ocean floor provides a record of Earth's magnetic field over millions of years, with stripes of normal and reversed polarity showing when new crust formed. The age of the seafloor increases with distance from mid-ocean ridges, confirming that new crust is created at these spreading centers and moves outward over time. Understanding volcanic islands and seafloor spreading has practical implications beyond scientific knowledge. The mineral deposits associated with hydrothermal vents include significant concentrations of valuable metals, and there is interest in eventually mining these resources. The heat from volcanic activity can be harnessed as geothermal energy, as Iceland has demonstrated effectively. These processes also affect global climate and ocean chemistry. Volcanic activity on the seafloor releases chemicals that influence ocean chemistry and provide nutrients that support marine ecosystems. The ongoing creation and destruction of ocean crust plays a key role in the carbon cycle and long-term climate regulation. The volcanic processes occurring on the ocean floor remind us that the Earth's surface is far more dynamic than the relatively stable ground we experience. Every continent, every island, has origins in volcanic activity, whether directly through eruption or indirectly through the processes of plate tectonics that volcanoes drive. Plate tectonics and volcanism. The theory of plate tectonics, developed in the 1960s, revolutionized our understanding of how Earth works and explained why volcanoes exist where they do. Before this theory, scientists could not adequately explain the distribution of volcanoes across the planet, or why earthquakes and volcanic activity clustered in certain regions. Earth's outer shell, the lithosphere, is not a single unbroken sphere, but is broken into about a dozen large plates and several smaller ones. These plates fit together like a jigsaw puzzle, covering the entire surface of the planet. They range in size from the massive Pacific Plate to smaller plates like the Juan de Fuca Plate off the Pacific Northwest coast of North America. The plates float on top of the asthenosphere, a layer of hot, partially melted rock that flows slowly over geological time. The plates are moved by convection currents in the mantle, circular patterns of heat transfer where hot material rises, cools, and sinks again. These slow but powerful currents drag the plates along, though the movement is incredibly slow by human standards, typically only a few inches per year. Three main types of plate boundaries exist, each associated with different geological activity. At divergent boundaries, where plates move apart, new crust is created through volcanic activity. At convergent boundaries, where plates collide or one slides beneath another, mountains and volcanic arcs form. At transform boundaries, where plates slide past each other, earthquakes are common but little volcanic activity occurs. Divergent boundaries are best exposed on the ocean floor along mid-ocean ridges. When plates separate, magma rises to fill the gap, solidifying to form new oceanic crust. This process, called seafloor spreading, has created most of the ocean floor we see today. The rate of spreading varies from less than an inch per year at some ridges to more than 6 inches per year at the fastest spreading centers. Iceland is the only place where a mid-ocean ridge is visible above sea level, providing a window into this process. Convergent boundaries come in several varieties. When two continental plates collide, they crumple upward to form mountain ranges like the Himalayas. When an oceanic plate collides with a continental plate, the denser oceanic plate slides beneath the lighter continental plate in a process called subduction. This creates deep ocean trenches, earthquakes, and volcanic activity. The Andes Mountains of South America formed from subduction of the Nazca Plate beneath the South American plate, and the numerous volcanoes along the western edge of the continent are direct results of this process. When two oceanic plates collide, the older, colder, and denser one subducts beneath the other, creating volcanic island arcs. The Japanese archipelago, the Philippines, and the Mariana Islands all formed in this way. The subducting plate dives into the mantle, releasing water and other volatiles that lower the melting point of the overlying mantle rock. generating magma that rises to form volcanoes. Transform boundaries occur where plates slide horizontally past each other. The San Andreas Fault in California is a famous transform boundary where the Pacific Plate slides past the North American Plate. At these boundaries, earthquakes are common, but volcanic activity is rare because the plates are neither creating new crust nor subducting old crust. The distribution of volcanoes on Earth directly reflects the locations of plate boundaries. Approximately 90% of all volcanic activity occurs along plate boundaries, with the majority along the Pacific Ring of Fire, a horseshoe-shaped zone that circles the Pacific Ocean. This region contains more than 75% of the world's active and dormant volcanoes, and is also the site of most of the world's earthquakes. The remaining volcanic activity, about 10%, occurs away from plate boundaries at hotspot locations. Hotspots are regions where unusually hot material rises from deep within the mantle, perhaps from near the core mantle boundary. Because these hotspots remain relatively stationary while tectonic plates move across them, they create chains of volcanoes. The Hawaiian Islands are the most famous example, formed as the Pacific Plate moved northwestward over a stationary hotspot. The relationship between plate tectonics and volcanism extends beyond Earth to other rocky planets. Mars appears to have stationary hotspots that created its massive volcanoes because it has no plate tectonics. Io's intense volcanic activity is driven by tidal heating from Jupiter rather than plate tectonics. Understanding this relationship helps scientists compare volcanic processes across the solar system. The plate tectonic theory also explains why some regions are volcanically quiet. The eastern United States, for example, sits in the middle of the North American Plate, far from any boundary, so volcanic activity has been minimal for tens of millions of years. The old volcanic rocks in that region are remnants of ancient plate boundaries that have since moved away. Plate tectonics continues to operate today, with constant movement of the plates, albeit imperceptibly slow. This movement ensures that volcanic activity will continue as long as Earth has an internal heat source, shaping the planet's surface and influencing the lives of the billions of people who live in volcanic regions. As our story slowly comes to an end, allow the final thoughts to fade. Gently into the quiet of the night, the rain and the calm ideas and the peaceful moments we've explored can settle softly in the background like distant echoes of a quiet evening. There is no need to think about anything now. Your body can continue to relax, breathing slow and steady. If you are still awake, simply remain here a little longer and enjoy the calm atmosphere. And if sleep has already started to find you, let it arrive naturally and without effort. Thank you for spending this quiet moment here on Cozy Sleep Time. If you enjoy these calm stories and gentle explorations, you can return anytime for another peaceful journey into rest. For now, let the night grow quieter and quieter and quieter, and allow yourself to drift deeper into sleep. Good night.